Somewhere right now, a team is 6 months into replacing RabbitMQ with Kafka, because Kafka is what the serious companies run. The migration will land, the new cluster will need 3 engineers to babysit it, and the system it replaced was never the problem. Nobody on that team can tell you, in one sentence, what all that work actually bought them. This video exists, so you're never on that team. 6 names come up in every one of these decisions: RabbitMQ, Kafka, SQS, Nats, Redis Streams, Pulsar. You can read 20-row comparison charts all week and still not know which one fits, because the charts never tell you which rows matter. One question sorts all 6. What does the system do with a message after a consumer reads it? Some delete it, like crossing an item off a to-do list. Some keep it, like a bank keeps every line in your statement. That one choice splits the field into 2 families, and once you see it, every one of the 6 snaps into place. We're going deep on all 6. How each one moves a message, what it promises, where it breaks, and the 2 failure patterns that cause real outages. One example runs through the whole video. A single order, number 4107, placed on a small web store, pushed through all 6 systems. By the end, you'll know which family your problem belongs to and which system to pick inside it. Start with the store, because every broker exists to solve the same starting problem. A customer clicks buy, and order 4127 is born. The payment service charges the card, and now 4 other systems need to hear about the order. Inventory has to reserve the item, email has to send the receipt, analytics has to count the sale, and fraud detection wants to score it. The obvious design is direct calls. The order service calls inventory, then email, then analytics, then fraud, and waits for each one. Now walk through the failure cases. If email is down, does the customer's order fail? If analytics takes 4 seconds, does checkout take 4 seconds? And if the first 3 calls succeed and the 4th one times out, the order service has to remember which 3 worked, retry just the 4th, and not double charge anyone while it does. You've quietly written a small buggy message broker inside your order service. Adding a 5th consumer next quarter means opening up the order service again. The fix is old and simple. The order service writes one message, order 4127 placed, hands it to a middleman, and gets back to taking orders. The 4 systems pick the message up from the middleman on their own schedule. That middleman is the broker, and each of the 6 systems in this video has a different opinion about how the handoff should work. First family, the queue, and RabbitMQ is its archetype. A queue works like a shared to-do list for your services. The order service pushes order 4127 into the queue. The broker holds it, picks a free worker, and hands it over. The worker sends the receipt, then replies with a small done signal, an acknowledgement. The moment the broker sees that ACK, it deletes the message. The task is finished, so the queue forgets it ever existed. If the worker dies before acking, the broker notices the dropped connection and hands the same message to another worker. A crashed worker never takes a task down with it. All the intelligence lives in the broker. RabbitMQ tracks every single message, which worker holds it, whether it was ACKed, whether it needs to go out again. Put 10 workers on one queue and each message still goes to exactly one of them. A slow worker just gets handed less because it asks for work less often. You get load balancing without writing any. That's the whole model. A task goes to one worker, gets done, gets forgotten. It has quietly run job queues, email pipelines, and background work for 15 years. The part of RabbitMQ most people never use properly is routing. Producers don't publish into a queue directly. They publish to an exchange, which is a small router in front of the queues, and rules you declare decide which queues get a copy. A fan-out exchange copies every message to every queue bound to it. That's how order 4127 reaches inventory, email, analytics, and fraud at the same time, each through its own private queue. A direct exchange routes on an exact label. A topic exchange routes on a pattern, so a consumer can say, "Give me orders.europe.anything," and only see European orders. Failure handling is built in too. When a worker rejects the same message too many times, RabbitMQ moves it to a dead letter queue. Think of it as a tow lot for broken messages. One poisoned order can't block the lane, and a human can go inspect it later. And one small setting that saves real pain, prefetch, which caps how many unacked messages one worker can hold. Set it to 1, and a slow worker can't grab 10 tasks and sit on them while other workers are idle. Now the corners of RabbitMQ that people find out about the hard way. Inside the broker, every single queue runs as its own tiny single-threaded actor with a private mailbox. That's why one broker can host 100,000 queues without blinking, and also why one giant queue tops out at roughly one CPU core. If a single queue is your bottleneck, adding cores won't help, splitting the queue will. Connections are the other quiet cost. A RabbitMQ connection is heavy to open and heavy to keep, so well-behaved apps open one connection and multiplex many channels over it. An app that opens a fresh connection per message can take the broker down all by itself. Watch out for the memory alarm. When the broker runs low on memory, it blocks every connection that publishes. If your service publishes and consumes over the same connection, the block freezes your consumer as well. Consumption stops, nothing drains, and the alarm never clears, so the whole thing stays wedged until a human notices. Always publish and consume on separate connections. Message expiry has a cruel detail in classic queues. An expired message is only actually dropped when it reaches the head of the queue, so setting a TTL doesn't save a queue that's already deep. The expired messages just sit there, holding memory, waiting their turn to be discarded. Last one. The old mirrored queue replication could lose acknowledged messages when the network partitioned, and it did, in production, for years. Modern RabbitMQ replaced it with quorum queues, built on the RAF consensus algorithm. If you're still running mirrored queues, plan the migration this quarter. Kafka is the archetype of the other family, and it's built on a different structure entirely, the log. Think ledger, a file you only ever append to. A Kafka topic is that ledger. Order 4127 gets written at the end, and it stays there. Nothing is crossed off. Consumers don't take messages out because nothing ever leaves. Each consumer just keeps a bookmark, a plain number called an offset, that says how far into the ledger it has read, and it moves that bookmark forward at its own pace. So analytics can be at entry 9 million while fraud detection is back at 8.5 million, reading the same data, and neither one affects the other. Reading deletes nothing. Entries expire on a schedule you pick, 7 days by default, or never, if you want to keep the full history. Notice who's smart now. The consumers carry all the state, and the broker becomes simple and fast because it only ever does the two things disks are best at: write at the end of a file and read a file front to back. No seeking around, ever. That's why Kafka's throughput chart looks absurd next to a traditional broker's. One ledger on one machine would cap you at that machine's speed, so Kafka splits every topic into partitions. This is the single most important mechanic in Kafka, so slow down here. A partition is just a separate lane, its own independent ledger on its own broker. Which lane a message lands in comes from hashing a key you choose. Give every event about order 4127 the key 4127, and they all land in the same lane, in the order they happened. For reading, workers join a consumer group, and Kafka gives each lane to exactly one worker in the group. 12 lanes and 4 workers means 3 lanes each. Add workers up to 12, and reading scales linearly. No locks, nothing shared. A second group, say analytics running next to fraud, gets its own lane assignments and its own bookmarks. The groups never touch each other. Durability comes from copies. Each lane has a leader and followers on other brokers. You can require a right to reach all of them before it counts. And when a broker dies, a follower takes over and the world keeps moving. Kafka's dark corners start with one that shocks people in design reviews. By default, Kafka does not wait for your message to reach disk before acknowledging it. A write with Axol is confirmed when it sits in the memory of 3 brokers. The disk write happens later, whenever the operating system flushes. The durability story is honest, just different. 3 machines and 3 racks, and the bet that they won't all lose power in the same second. Kafka also barely uses its own heap. The real cache is the operating system's page cache, so a healthy broker serves most reads from memory that its own code never touches. There's also a reason encryption hurts more than people expect. Normally, Kafka moves outgoing bytes straight from the page cache to the network socket with a single system call, send file, so the data never even passes through Kafka's own code. That shortcut is a real chunk of the speed. With TLS enabled, it's impossible. Every byte has to come up into user space to be encrypted, and clusters lose a noticeable slice of throughput the day security turns encryption on. If nobody on the team knows about zero copy, that regression gets blamed on everything except the actual cause. Log compaction is the last one, and it changes what a topic even is. A compacted topic keeps only the newest entry per key and throws the older ones away, which turns the ledger into something closer to a table of current values. Deleting a key works by publishing a null for it, Engineers call that a tombstone, and once compaction runs, the key is gone from the topic. Those two designs fork everything downstream. In the queue family, a message is handled once, and then it's gone. Fanning order 4127 out to inventory, email, analytics, and fraud means 4 physical copies in 4 queues, and all 4 had to be declared before the message was published. The broker can't deliver to a consumer it didn't know about. Ship a new service next month and it starts blind because the history it needed was deleted as it was processed. In the log family, the entry just sits in the ledger. A new consumer shows up 6 months later, sets its bookmark to 0, and reads the whole history as if it had been there from day one. That replayability is worth being concrete about. Your search index got corrupted? Rebuild it from the ledger. You shipped a pricing bug in March and fixed it in May? Rerun March through May through the fixed code. Data science wants 2 years of orders? Point them at the topic. All of those are the same operation, read from the beginning. Deletion buys you simple work distribution. Retention buys you replay. Before the other 4 systems, we need some vocabulary, because 3 delivery guarantees decide whether a system silently loses data or silently duplicates it, and every broker picks from the same short menu. At most once, at least once, exactly once. None of them is called perfect, and there's real math behind that. When the network itself can drop packets, a sender and a receiver can never be completely certain the other side saw the last message. Computer scientists proved this decades ago as the 2 generals problem. So every delivery guarantee is really a decision about which direction things go wrong in. At most once means the producer sends and never checks. If something crashes mid-flight, the message is gone. For an order, that would be malpractice, but plenty of data doesn't deserve a guarantee. A temperature sensor that reports every second can lose a reading without anyone caring because a fresher one is already on the way, and skipping all the confirmation machinery makes this by far the fastest mode. At least once is what acknowledgements buy you, and it's the default nearly everywhere. It has one sharp edge, and our store walks right into it. The email worker sends the receipt for order 4127, then crashes 1 millisecond before it can act. From the broker's side, a crashed worker and a slow worker look identical, so it plays it safe and delivers the message again, and the customer opens 2 receipts. Duplicates come with at least once delivery. Every system built on it produces them eventually. Exactly once is what everyone wants, and inside a single system Kafka can genuinely deliver it, with transactions that keep produce and consume in step. What it can't do is reach outside itself. The moment a side effect leaves the broker, an email, a card charge, a call to someone else's API, the guarantee ends at the boundary, and your code has to pick up the rest. The standard tool is an idempotency key. The charge for order 4111 carries its order ID, so if the same charge arrives twice, the second attempt matches the key and quietly does nothing. Stripe works this way, and so does every payment system that survived contact with production. Now the rest of the field. SQS is Amazon's managed queue, same delete on ACK family as RabbitMQ, with nearly every knob removed. Its core mechanic is the visibility timeout, and it replaces the whole ACK connection. A worker receives order 4127, and the message stays in the queue, but turns invisible 30 seconds by default. Finish the job and delete it, done. Crash, and the timeout runs out, and the message simply becomes visible again for the next worker. No connections to track, nothing for the broker to remember about you. You get 2 flavors. Standard queues are roughly ordered and will occasionally hand you a duplicate. FIFO queues give you strict order and deduplication and cap your throughput in exchange. Under the hood, it's a big distributed system wearing a queue costume. Your message is stored on many servers at once, and a receive call samples only some of them. That's why a poll can come back empty while the queue clearly has messages. You sampled the wrong servers. 2 billing realities follow. Long polling, where a receive call waits up to 20 seconds for a message, fixes the empty poll problem, and you want it anyway, because SQS charges per request. A fleet of workers hammering an empty queue with short polls is paying Amazon to be told no. If you know Kafka, one mapping makes FIFO instantly familiar. The message group ID is a partition key with a different name, the same ordering unit. Deduplication only looks back 5 minutes, and payloads cap out around a megabyte, so big payloads go to S3 and the queue carries a pointer. Latency runs tens of milliseconds instead of 1, and the trade is honest. You give up routing, priorities, and control, and you get a queue you'll never patch, resize, or get paged for. On AWS, if you need a task queue and not a platform, SQS is the boring, correct default. NATS is built for one thing above everything else: speed. Its radical default is that it doesn't persist anything at all. Run the store on NATS, and the order service publishes 4-1-27 to the subject orders .placed. Everyone subscribed at that instant has it within microseconds. Nobody subscribed? Then the message is simply gone, by design. Subjects are hierarchical, so fraud can subscribe to orders.anything with a wildcard, and a refund handler can listen to orders.refunded and nothing else. Services can also call each other through it. Request reply over the same wire, so inventory can answer, "Is this in stock?" with no HTTP service in between. The whole server is one small binary that pushes millions of messages a second, which is why teams use it as the nervous system inside a platform. Service-to-service messaging, control planes, fleets of devices. For our store, there's an obvious catch. If the email service is down at the instant 4-1-27 is published, the receipt is just gone. When that matters, you turn on Jetstream, the persistence layer that adds storage, replay, and at least once delivery on the same server. The protocol is plain text, and that tells you a lot about the culture of the thing. You can open a raw socket, type suborders .placed by hand, and watch messages arrive as readable lines. Its self-protection is the opposite of RabbitMQ's. Where RabbitMQ blocks producers when it's under pressure, NATS disconnects any consumer that reads too slowly and keeps serving the fast ones. The server protects itself first. The philosophy is messaging as plumbing. So light you stop thinking about it, where dropping a message beats making everyone wait. Redis Streams is the log family in miniature, the same shape as Kafka, living inside a database you probably already run. Order 4127 becomes an entry appended to an order stream, stamped with an ID that encodes its position, and it stays there after everyone reads it. Email, inventory, analytics, and fraud, each read through a consumer group with its own bookmark, just like Kafka's groups. And if the email worker crashes mid-receipt, the entry doesn't get lost. It sits in a pending list, and another worker can claim it and finish the job. A new consumer can still replay from the beginning. The ceiling is the difference. The whole stream lives in one Redis node's RAM. It can't be split across machines, and retention is a max-length cap, not a 7-day policy. Two practical details save real pain. When you cap the stream, use the approximate flag, the tilde. It lets Redis drop whole chunks at once instead of trimming entry by entry, and it's dramatically faster. And be honest about durability. Redis replication is asynchronous, so a failover can lose entries that were already acknowledged, and the default disk persistence can drop the last second of writes. It's a real log, with Redis durability. Size your trust to that. But the cost column wins arguments. If Redis is already in your stack, a real event stream costs you 0 new infrastructure. At thousands of orders a second, that beats standing up a Kafka cluster every single time. Pulsar is the one system on the map that refuses to pick a family. Underneath, it's a log like Kafka, but it adds per-message acknowledgement on top, so a single topic can serve both families at once. Watch order 4127 do both jobs on the same topic. The email workers share a subscription, queue style. Exactly one of them gets 4117, acts it, and it's retired from their view. Meanwhile, analytics reads the same topic log style, keeps its own bookmark, and can replay history whenever it wants. 2 models, 1 copy of the message. Serving both sides has a bookkeeping price you can picture. With individual acts, a consumer can have acknowledged entries 5 and 7, but not 6, so Pulsar's cursors track ACK holes, little gaps in the acknowledged range. A pure queue never needs that, a pure log never needs that, and maintaining it is the tax Pulsar pays for doing both. The architecture splits compute from storage. Stateless brokers answer traffic in front. A bookkeeper cluster owns the data behind them, so adding a broker is instant, nothing has to move, and old entries can be tiered off to object storage like S3, which makes keeping every order the store has ever taken affordable. The price is operations. It's 2 distributed systems to run instead of 1, and that's the whole decision. If you truly need queue and log semantics at scale, on one platform shared by many teams across regions, Pulsar earns its weight. Below that, it's overkill. 2 traps, 1 per family, and you sign up for one of them on the day you choose. On the queue side, the trap is backpressure. The broker holds every unprocessed message, so a slow consumer literally becomes broker state. Here's how it plays out. The email provider has an outage. The email service processes nothing for an hour, and orders keep flowing. The queue grows to 10,000, then 10 million. Deep queues make the broker itself slow, and when RabbitMQ hits its memory limit, it starts blocking publishers. Now the order service, which is perfectly healthy, can't publish. Checkout is down, and the root cause is an email vendor. That chain is the trap. The defenses are boring and they're mandatory. Alert on queue depth and on message age, not just on consumer errors. Give queues a max length so they shed the oldest work instead of syncing the broker, and decide per queue in advance, which is worse, dropping work or blocking producers. Under sustained overload, you'll be doing one of them. The log side trap is ordering, and it hides for months. Kafka guarantees order inside one lane and nowhere else, and the lane is picked by your key. Use a lazy key or no key, and the refund for order 4127 can land in lane 2 while its payment sits in lane 7. A consumer can process the refund before the payment. Nothing throws, no error anywhere, the numbers are just wrong. And because two related events only collide when they hit different lanes at the wrong moment, it works in the demo, works in staging, and bites in production in month 3. The rule that saves you? Everything that must stay ordered shares one key. In our store, that's the order ride. The second thing to watch is lag, the distance between the end of the ledger and a group's bookmark. A consumer group that's falling behind looks completely healthy on CPU graphs, so you monitor lag directly and treat it with the same urgency as a growing queue. Adding lanes looks harmless and isn't. Keys map to lanes by hash modulo, the lane count, so growing 12 lanes to 16 silently reroutes most keys and breaks per key ordering across the change. Plan lane counts the way you plan database schemas, and when one consumer stalls too long, Kafka ejects it and redeals its lanes. The whole group pauses while that happens. Then the stalled consumer recovers, rejoins, and the group pauses again. That loop is a rebalance storm, and static membership and cooperative rebalancing exist specifically to calm it. So here's the decision, compressed to 2 questions. Question 1, is your message a task or a fact? A task is done once and forgotten. Resize this image. Send the receipt for 41,127. Tasks belong to the queue family. Delete on ACK. A fact is something that happened, order 41,127 was placed, and facts get read by many systems for a long time. Analytics counts it today, the fraud model retrains on it next month, finance reconciles it at the end of the quarter, facts belong to the log family, retain and replay. Question 2, how much system do you actually need? In the queue family, SQS if you're on AWS and want 0 operations, RabbitMQ when you need real routing, priorities, and dead letter flows, NATS when latency is the product and a lost message is survivable. In the log family, Redis Streams when volume is modest and Redis is already there, Kafka when the stream is the backbone of the business, Pulsar when you truly need both families at once and can pay for it in operations. Then find your family's trap, backpressure or ordering, and set up its alarm the same week you deploy. Waiting for the first incident is how these traps stay traps. One order went through 6 systems. RabbitMQ rooted it and forgot it. Kafka wrote it in a ledger and kept it. SQS hid it for 30 seconds at a time. NATS delivered it in microseconds or not at all. Redis Streams kept it as long as memory allowed. Pulsar handed it to one worker and let another replay it. Same message, 6 lives, and every difference traced back to one question. So stop asking which broker is best. Ask what your message is. Tasks, done once and forgotten, live on the queue side, with RabbitMQ, SQS, and NATS. Facts, events with many readers and a long life, live on the log side, with Kafka, Redis Streams, and Pulsar. One design decision, delete on read or retain and replay, draws the whole map. Every feature matrix you'll ever read is downstream of it. If this saved you from a 6-month migration in the wrong direction, the like button is right there, and subscribing gets you the next deep dive into a system everyone uses, and few can whiteboard. See you in the next one.